Hello everyone, welcome to this video. My name is Sentinel-2. I'm a Google Earth Engine expert. In this tutorial, I'm going to show you how to calculate carbon stock for vegetation area using Google Earth Engine platform and regression technique. In the first step, you must select your region of interest. It is better your region of interest covered by forest or agricultural area. For example, in this tutorial, I'm gonna select a region in the north of Iran, including agricultural area and also the forest here. As you can see, this part of Iran in the north, it's a good place for me to study because I know this region. You can use this tutorial for all around the world and don't limit yourself to the region I'm working. The satellite data I'm utilizing in this video publicly available for all around the world, and easily you can select your own region and apply this method. So in the first step, I'm gonna select the province I'm gonna work on using search places and dataset. If you don't have the province shapefile, no worries. In the Earth Engine, FAO administrative layer are available. As you can see, the FAO administrative layer with simplified version is available. If you're gonna work on the provinces, the first level suggested. Import it into the code as a separate table, and now use the map.add layer to visualize the table to see what's inside in the table layer. As you can see, all regions recognized by administrative borders, the first level or province. So for example, I'm gonna work on this region because it is covered by the forest and agricultural area. So there is a very simple technique. You must just mark your target and then filter the table based on the location. Make a new variable as ROI or region of interest equals to, now we must filter the table based on location of selected point already named as a geometry here. Get rid of the previous map.add layer and make a new one based on a ROI. Map.add layer based on ROI and map.center object based on a ROI again. So center object allows you to focus on the ROI, and add layer will visualize the ROI or your region of interest. Run a code. After a few moments, you will see the province you want to work on. So this is about your region of interest. There are other shapefiles or layers in the Earth Engine that you can define your region of interest based on. For example, you can select a country, you can select a province, you can select a city, or if you want to use the basin layer, you can try with a hydroshed layer level 5, or different level of basins here is available and allows you to select your region of interest based on the basin border. It's totally up to you based on which kind of layers you want to select your target of interest. So in the next step, we need to call the necessary satellite data. So if you go to search places and dataset and type for example, carbon stock here, there are a lot of products available, but all of them limited to a single year. For example, one of them is WCMS, above and below ground biomass carbon stock layer, that allows you to get carbon tons per hectare for each region with 300 meter spatial resolution. But there is one limitation. It has a low spatial resolution, 300 meter, and also it is only available only for 1 year. But the good news is it is available for the whole of the world, but limited to only one single year, 2010. And now you cannot use this product for 2020 or 2012 or 2000 earlier and later. You will have a lot of problems to get estimate about the carbon tons per hectare or you will face with a lot of challenges for biomass estimation. Now I'm going to show you how to use regression analysis, make a model between this product and Sentinel-2 bands allows you to estimate or have a better estimation of carbon stock for the rest of the years with higher spatial resolution. That could be a very, very popular tutorial and topic in the vegetation-related studies. So, first, import it into the code as a single image collection. Make a new layer as a carbon, as you can see, equals to image collection. We are assigning image collection to the carbon. And now, print out carbon to see how many images available under an image collection. Only one element, one image is available for the whole of the world. But for the further analysis, we must convert it from image collection format to image structure. That's why we need to select the only image available in this product using the first function. Remember to save your code and run it again. After a few moments, so as you can see here, again, you have the same image, but this time with image structure, no image collection anymore. So now we have an image for carbon belongs to 2010. Let's get a visualization for the region of interest using map.add-layer. Map.add-layer carbon that is clipped based on a region of interest or ROI. Leave the visualization parameters empty and go to the layer name and enter here carbon stock. So use the false at the end to avoid automatic visualization. Run a code. After a few moments, you will have a new layer as carbon. If you click on, you can see the carbon layer for your region of interest. Increase the contrast through the setting and 90% of values available in this product. Click on apply and here you can see the carbon stock value for the forest, and here that shows very well. So switch on inspector to see the pixel values. As you can see, for example, the selected pixel has 59 carbon stock, or the 59 here means if you go to the data characteristic, the unit is based on carbon tons per hectare. This pixel returning 59 carbon tons per hectare during a year based on actually the biomass and the volume of vegetation cover in this region already estimated. So, and here is the description about the product. Now I'm going to show you how you can calculate this parameter, but for the forest region using Sentinel-2 with higher spatial detail. So to do this, first you must call Sentinel-2 data. Go to search places and dataset and type for Sentinel-2. Two kinds of products from Sentinel-2 are available, level 1C, level 2A. Level 2A is preferred because it is already corrected radiometrically and atmospherically, and it is the best choice for vegetation-related indices or calculations. Make a new variable as Sentinel-2 and then assign a second image collection to Sentinel-2 variable. When you are dealing with an image collection such as Sentinel-2, you must filter your data based on a region of interest and based on a period of time. That filter bound allows you to filter your data based on an ROI region, and then you must filter your data based on a period of time you want to have carbon for. For example, I'm going to calculate the carbon for 2020. Here, the filter day starts with from 2020 and ends to 2021. So, let's get a print to see how many Sentinel-2 data is available. In the right panel, switch to console And here you can see around 1000 images available for this region. If you go to the data properties, for each image we have 26 elements, but the only multispectral bands, band number 1 until band number 12, can be used for the carbon modeling. And also there are the other parameters in the metadata file allows you to filter your data based on a cloud coverage. Here, as you can see, the cloud pixel percentage already calculated here, and we can call those of satellite data with the lowest cloud cover that is possible. It is very easy to do. That filter, make a new filter, less than filter inside the main filter allows you to filter your data based on cloud cover percentage. For example, I'm gonna have those of Sentinel-2 data in which cloud cover is less than 10% because I'm gonna make a cloud-free mosaic layer for this region that will be an input for the regression modeling in the next step. If you run a code based on the new filter in the right panel, you will see only 275 elements in which cloud cover is less than 10% over 2020. Now I'm going to calculate a median for the whole of the year. That median, the median compared to the average or mean allows you to get an average without without extreme values impact coming from satellite noises or atmosphere impact. So the median image calculated, but if you go to the data properties, here you will find scale factors suggested for all the bands of Sentinel-2A, Sentinel-2 level 2A. That's why we must multiply multispectral bands to the scale factor suggested by data description. It is very important to apply the suggested scale and offset values on satellite data before further processing, because it allows you to actually convert your data to original range of values that should be for the further analysis. So now we will have one mosaic cloud-free Sentinel-2 images. In the next step, it is very important to calculate some spectral indices such as NDVI allows us help us to have another helpful predictor for the carbon estimation. Remember that here I'm gonna use a regression model. When you are dealing with regression analysis, it is very important to have multispectral bands with some spectral indices as a predictor, and the original variable is carbon. Using the predictor, for example, the multispectral bands and spectral indices, we can find the amount of differences between these values and estimated carbon for the region of interest, and then we can apply that model for different period of time. So here the multispectral band already provided. Make a new variable as NDVI, normalized difference vegetation index, so the most popular vegetation index or spectral index in the remote sensing community that allows you to do very interesting analysis regarding to the vegetation cover, whether in agriculture or the forest area. NDVI equals to, from Sentinel-2 multispectral band, I'm gonna calculate the NDVI. Before that, let's get a print from Sentinel-2 data to get a better understanding about the nature of Sentinel-2 images. As you can see, we have one image with 26 bands, but as I mentioned earlier, we must filter the bands based on multispectral data. Here, that select allows you to select your target bands starting with B, and the rest is not matter. Run a code again, and this time you will have an image with 12 bands starting from B1 ends to B12. All the bands available here, and now you can calculate the NDVI. Make another variable as NDVI. get Sentinel-2 data. Through the normalized difference, you can calculate the normalization relationship between band number 8 as a near infrared and band number 4 as the red band. Normalized difference band between band 8 and band 4 here, band 8 and band 4, and rename the output as NDVI, just like that. And it is better to use the brackets for the input bands here. Let's get a print from NDVI images for the region. In the right panel, we will have one NDVI that is calculated, or you can visualize the NDVI image to get a better understanding about NDVI variation over your region of interest. Map that add layer again comes, and here this time we want to show the NDVI that is clipped based on ROI and leave the visualization parameters empty. The layer name could be NDVI and use the false at the end to avoid automatic visualization. Remember to save your code and run it again. Here in the right panel, you will have NDVI image for your region of interest. It is very important to have a cloud-free NDVI for your region. And in the original image, as you can see, in the original carbon stock image, if you increase the contrast, definitely you can see the carbon value only for the forest region because they are stable compared to actually the agricultural area that varying from one time to another time. That's why I'm suggesting you to make a mask based on and remove the regions and remove the non-vegetation areas from input images. That gives you a better understanding and helps you to estimate more accurate the carbon stack for the target land cover, that here it is the cropland. So let me to actually make a mask and clip the predictors based on the land cover, because I'm gonna have the, for example, I'm gonna have the forest land cover in the predictors and get rid of the other land cover. The simplest way is to use the land cover products available in Dynamic World. Type for Dynamic World. The Dynamic World, as you saw on my YouTube channel, is one of the popular land cover data multi-temporal. Land cover data, it is available with 10 meter spatial resolution developed by Google here, and you can filter out, you can actually have a land cover layer for your region of interest easily for the years after 2000, I think 2015 or 2017. But here you can go to the data properties, and yes, there it is. It is available since 2015 with weekly temporal frequency. And if you go to the bands, you can see it has 10 meter spatial resolution and different classes is available. But the target class here is the forest. We can find it, and we can find it to see, yes, here there is a trees, and we can actually keep the trees and get rid of the other classes for the further analysis. So let's back to the code and import the Dynamic World into the code editor environment as a third image collection. So Dynamic World dm equals to image collection third, the third image collection assigning to the dm. And now I'm gonna filter this image collection based on a region of interest and period of time that is target. The filter date starting from 2020 and to 2021. Get filter bound. I'm bounding the data based on ROI here, and then I'm gonna find the most frequent classes in this region, and let's select the target band that here it is a label. Just like that, you will have a label as a target class here, and now print dm Dynamic World dw. It should be dw, not dm. Sorry for the mistake. Yes, dw. we will have one image. A mode image actually returns the most frequent classes during a year because it has a multi-temporal characteristic. So go to the data characteristic here to see which value in the label. As you can see, the label includes all the classes, but here the trees is the target class, and we want to actually select pixels including tree. So here the w dot equal pixel value number 1. Let's make a visualization from dynamic word for our region of interest and leave the visualization parameter empty, and the layer name could be tree, and use the false at the end to avoid automatic visualization, because automatic visualization reduces the speed of processing. So click on tree, and now you will have a binary image that shows only trees, or actually the forest in your region of interest. And this is a very, very valuable product. Allows us to mask out the rest of the classes from NDVI and predictors we have. For example, the Sentinel-2 NDVI and the rest of the things. So here I'm gonna make a variable as predictor equals to the predictors is a the predictors is actually a stack layer including a constant value, Sentinel-2 multispectral band, and also the NDVI calculated. Let's make a constant image first. Engine.image.constant. I'm gonna have a constant image including value 1 that is necessary for the linear regression method. So next I'm gonna actually have the other predictors that add bands that could be multispectral bands already stored in Sentinel-2, and also the NDVI images, and also the NDVI image. Here, if I make a print from the predictors, you will find a single image in the right panel including 14 bands. These are the predictors we want to use to predict the carbon stock for the region of interest. So, and then it is important to actually mask out the rest of land covers in all predictors through the update mask. The update mask based on dynamic word layer. Now let's get a print from predictors or visualization from predictors. Here we will have predictors already clipped based on the region of interest, visualization empty, and the layer name could be predictors or anything else you prefer, and use the false at the end. Remember to save your code and run it again. After a few moments, predictors added to the layer. Click on one of the predictors. Various predictors are available. For example, I'm gonna see the NDVI image where based on 90% of values. Here, click on apply, and after a few moments, you will have NDVI value only for trees and forest region. So as you can see, the rest of cover is actually removed, and there it is. So now predictors are ready. We must actually merge the predictors and original variable that is carbon stock together, and then make a linear relationship model. So here, make another variable as dataset equals to. First we will have the predictors, then carbon stock will add through the add bands. Get a print to see everything works well. Print out dataset. In the right panel we will have a new dataset with 15 bands. The last of them is the carbon tons per hectare, as you can see. Now we must make a model based on actually the dependent and independent variable. So, and make a new variable as a model equals to. Get the data set first, and then through the reduce region you can actually make a model based on region of interest. Reducer allows you to actually define a different statistical operator. The target statistical operator here is a linear regression method, Earth engine.reducer.linear regression, just like that. Linear fit already addressed in the previous tutorial on my YouTube channel. You can go to that video and see the tutorial. But in this video, I'm going to show you how to use the linear regression. Here we will have predictors and also the original parameter. The predictor we have 14 predictors here. We have 15, but 14 of these bands from constant to NDVI belongs to X, or they are actually the predictors for T, and Y will be actually the carbon per hectare, the target band here. We want to find their relationship based on a region of interest that is defined as a ROI and spatial resolution, that is a scale based on a scale value or grid structure that should be 250. The scale should be, for example, value between 10 and 60 based on a spatial resolution we have in the Sentinel-2 data. But when you select a large region of interest, definitely you will face with a lot of issues such as user memory limit exceed and something like that. That's why I'm suggesting you to reduce the resolution for actually making a model for your region of interest to avoid such kind of errors during the processing, and use the best efforts to have the best estimation for your region of interest. Make it true. It is a Boolean parameter. So the model now is created. Let's get a print to see how model works. Now we expect to have a scale and offset explaining the differences between the predictors and carbon stuff or original variable based on a region of interest and based on other parameters we already settled here. So dictionary is under computing. It's a bit longer. You must be patient here because you have 15 bands for a large region that definitely is needs more time to process and return the final results. During this time, remember to save your code and wait until you get the final scale and offset from the dictionary. It is very important to get the coefficients for converting the dataset or predictors to carbon stock. So if you had any problem regarding to the codes, it should be noted that the code link is available below the video on my YouTube channel in description box, and you can find it and compare yours with mine. And if the problem still exists, you can reach me out on YouTube channel. Here, as you can see, the coefficients calculated based on predictors, and also the residual is also calculated. Now we want to actually get a coefficients inside in a list structure and then apply it on the predictors to get estimation for the carbon stock based on Sentinel-2 data. It is very easy technique. Just make a new variable as a coefficient here. Coefficient equals to here, and make an array structure because it has an object structure, Earth engine.array. Now make array and bring the model here and get the coefficients values. Here a dictionary structure and object structure. We have some keys and we have some values, and when you want to select something such as coefficients, here you must use the get in such kind of a structure. Get coefficients, and then after coefficients selected, we can project, or before that you can print what is coefficient to get a better understanding about its working. So as you can see, we converted into a list with 14 elements, but must be projected into a single list and without, because we want to get rid of the keys here. That's why we want to project it based on a first dimension. Here it is. And finally, I'm gonna convert it to a list, bring it into a list structure. And now you will see a list of coefficients available. 14, its length depends on the number of x or number of the predictors. So after coefficients prepared, now we can calculate the carbon value, the carbon stock for Sentinel-2 data. So here we want to actually calculate Sentinel-2 carbon equals to, bring predictors first and then multiply them to the image including these values. Earth engine.image.constant. I'm gonna have image constants including these values here based on coefficients, and then calculate their sum value using Earth engine.reducer.sum. So as you can see, through a constant, we converted the coefficients from a list to single images that is multiplied to the predictors, and then we calculated their value, their sum of them, or aggregated by sum. So the output will be one image and including carbon stock value with higher spatial resolution based on Sentinel-2 data that we have. So let's get a print first to see if everything works well. Sentinel-2 carbon, one single image returned. Better to rename it to Sen2 carbon and run it again. In the right panel, collapse the image, and here, or expand the image, here you can see the Sentinel-2 carbon estimated. Let's visualize the output through the map.add layer. Sentinel-2 carbon that is clipped based on the region of interest, ROI. Leave the visualization parameters empty, and the layer name is Sentinel-2 carbon, and use the false at the end. Run a code and remember to save it. Sentinel-2 carbon estimated. And now you can visualize it for forest region, same as the original image we already had. I'm waiting for the visualization of output. You can increase the contrast through the 90% of values you have for your region of interest. The negative values related to the noises that you can get rid of them by a simple thresholding method. No worries about the negative values. Click on apply, and here you will see variation, carbon stock variation with higher spatial detail compared to original one. This is the original product. You can increase the contrast. Here it is. And this is our prediction. So switch to inspector and click one pixel. Same time, you can see the carbon tones per hectare is 37 for the selected pixel, and also it is a 63 for the selected region. As you can see, somewhere, some areas we have very actually overestimations, or maybe for the other areas we have underestimations. So as you can see, for example, in this pixel, it is closer. The original value was 56. What we estimated is 60. And also the actually accuracy varies from one point to another point in this region. So Now you can actually calculate the amount of the RMSE, explaining the differences between the actual values and predicted values easily. So first of all, we must calculate the differences between predictor and between the predicted values and actual value. The actual value, the original value was carbon subtracted from the predicted value, that is Sentinel-2 carbon here. And then calculate power 2 here, bring differences to square it. So here differences reach to power 2, and then we can get its average for the whole of the region. Finally, the RMSE equals to bring POW, reduce region, and calculate its average. So here, reducer, Earth engine.reducer, get average, geometry, region of interest equals to ROI, and scale should be 250 here. So to get the values, use the dot values and get the first item here. Convert it to a number structure using Earth engine.number. Finally, calculate the SQRT. So to get a square root of the differences, print RMSE, and run a code. Remember to save the code, go to the console, and here you can see the RMSE value estimated for the region of interest. As long as RMSE closer to the 0, meaning that we have a higher accuracy, and as much as RMSE go far from the 0, meaning that we have large differences between original and predicted value. There are a lot of ways to increase the accuracy. One of them is change the actually combination of the predictors and use another regression methods. These are important parameters, allows us to increase the accuracy of estimations. Now be patient for a moment to get the RMSE value for your region to see how, and also the RMSE could be vary from one region to another region. Again, actually, if you had any problem regarding to the code, suggesting you to back to my YouTube channel and find the code example there. So here the RMSE is 17, meaning that we have 17, we have 17 tons per hectare differences between predicted value and the actual value we had. And as I mentioned earlier, the final accuracy depends on a couple of things. One of them, region of interest. For example, in the heterogeneous area, you will have a higher accuracy, you will have lower accuracy. For homogeneous area, you will have higher accuracy. It depends on the region of interest. It depends on the bands combination. Maybe you increase the diversity of the bands or the input bands, use the more spectral indices, or use the most various parameter, more actually different parameters as a predictors, then you may have higher accuracy. And also the regression method is also important. In addition to the linear regression, other actually regression method is also available. For example, robust linear regression is another regression method that you can try for to see how much differences you will have between this method and the previous one. You can actually change these parameters in your model to see how it works, and also how the code reaction to different parameters, and then try to increase the accuracy for your region of interest. And finally, I'm going to show you how to save your final results, that is Sentinel-2 carbon. That is very easy, and just you must export using export image to drive. here couple of arguments necessary for exporting process. One of them is the target image you want to get export is Sentinel-2 carbon. Suggest you to convert it to a real value through the float and clip it based on the border of region you are working. So get clip based on the ROI, and the description explains the output file name. For example, the output file name is Sentinel-2 carbon. Scale refers to the grid size for the output, and RMSE again calculated. Not a big differences between a robust method and simple linear regression. And also, if we may change in the band combination, maybe the accuracy change from one location to another location, it's totally up to you. And also you can go to the literature and find the best combination for carbon stock estimation. At least it is a good method to fill the gaps for the carbon stock value from one year to another year. And if I want to be honest, it is not really actually comparable, the value for 2020 with values for 2010. The RMSE should be calculated in case we have 2010. Our predictor belongs to 2010. In that case, the RMSE could be meaningful because the condition of the forest and also the vegetation cover 10 years after the original image definitely is different. And because of the limitations of multi-temporal carbon stock value, I had to use actually such kind of variations in this tutorial. That's why I don't suggest to actually compare value 2010 and value 2020 because their situation is totally different. Just here mentioned the methods to how to calculate the RMSE. And a scale equals to, so value, for example, 100, because the spatial resolution for the output varies from 10 to 60 in the Sentinel-2, but I prefer to select 100 because the region of interest is very big compared to the original value with 300 meter spatial resolution. Actually, now still we have a good accuracy for the output. So the region of interest, the output you want to get export here equals to the ROI, and the other parameters such as, for example, yes, the target folder you want to save your data in could be anything. For example, I'm going to make a folder as test on my Google Drive, and the CRS explaining the coordinate system that should be WGS84. Its code is EPSG4326 in the Earth engine, and the CRS value is same for all around the world, no matter where is your location. Just you can use this code for the whole of your region. This is about the CRS, and the other parameters here, the scale, CRS already, and also the maximum pixels. Yes. The maximum pixels for the output should be equals to 1E30. So everything settled, save your code and run it again. Go to the task. After a few moments, Sentinel-2 carbon is ready for saving. Click on run and wait until the process of saving is over. Once the tab's color turns to the blue, same as before example, meaning that the product saved successfully and you can pick it up from your Google Drive. I hope you like this tutorial, and if you had any problem regarding this tutorial, you can reach me out on my YouTube channel. On my YouTube channel, you can have access to around 100 tutorials about Google Earth Engine platform using JavaScript, and all of them available from basic to advanced methods. And I hope you like this tutorial, and feel free to reach me out on YouTube channel and put your comments and share the tutorials with your community. Thank you for your attention.